Hi, I've done it. I'm running a C compiler natively on the microcontroller, specifically on RP2350. So how did I achieve this milestone? The first step was creating a cross-compiler. I briefly covered this in my previous video, so if you haven't seen it yet, I highly recommend checking it out. To set up the environment, I use a script that prepares the necessary tools, builds the tiny C cross-compiler, and then generates the root file system for the target hardware. At this stage, I also need to integrate the process of building a native compiler for YASOS. So looking inside the build rootfs script, we have the following recipe. First, building a tiny C compiler. Then with use of cross-compiler, system libraries are produced. Having both cross-compiler and libraries means we are ready to produce native compiler. Native compiler uses native system libraries. That's why they need to be built as precondition. Looking inside code, you can spot that for cross-compiler and tiny C compiler, exactly the same code is in use. With this setup, I can now use the native compiler directly on the target hardware. Compilers are highly complex pieces of software. They are also excellent at self-testing, since they rely heavily on their own functionality. In other words, a compiler should be able to generate itself correctly. So running compiler directly on my board uncovered a few bugs in my tiny C support for ARM version 8M architecture. Debugging a compiler is both challenging and straightforward. If you understand assembly and target hardware architecture, it's fairly easy, but if not, then it may be overwhelming. Let's start with the first issue. My cross-compiler failed to produce native compiler with an error with too far address. So I've enabled debug logs and started digging in. The first note worth mentioning is fact that the last instruction was at position 690C in hexadecimal. It is a patch of call, which means that bug is somewhere in jump instruction generation. I have if here to select branch instruction from 2 or 4 bytes. Let's modify it to always choose 4 bytes. It will be less optimized, but always working, at least for now. And now we discovered another issue with file declaration. Oh, I forgot the header guard. That explains everything. The next crash was more challenging, so using debug prints GDB commenting parts of code, I've discovered that compiler crashes when it is inside OT-check function. I found out that OT-check is different from other functions only because it takes struct as an argument, and the problem occurs when the struct argument is passed at least by 2 functions. So I've created a simple example code just to recreate that issue and to reduce code necessary to analyze that problem. So I decided to add print statements wherever vstack is incremented or decremented. Vstack is a tiny C compiler internal structure to keep necessary data. Tracking the path inside GDB, I found a place where I called the vstore function twice. And this was the root cause of that bug. Fixing this single issue led to successful compilation of CrashMe example. Now it was the time to disable debug logs and move forward with the porting process. And wow, I was impressed. I've now encountered an error from the linker rather than the compiler, which is the next step in the build process. The build failed when linking libm, which wasn't really unexpected. I don't have libm at all. So let's add one, but only the missing symbols required for tiny C. A full implementation of libm is a separate challenge. Then I've added dozens of missing symbols to my standard libraries. But most of them were just stubs, without any real implementation. So how it is possible that I have dummy implementations that does nothing and compiler is working? And this is because tiny C has the ability to run C scripts similarly to shell scripts. So you can run C source files. The assembly compilation has failed, though I was unsure whether these components are actually used in the cross-compiler, because this one should fail when compiling cross-compiler, yeah? And right, I should probably configure make to build only the native compiler for my architecture. After fixing the flags, I uncovered further problems with the cross-compiler. Oh well, we've definitely hit an infinite recursion. This issue arises because store is called due to a lack of free registers. The offset is too large for an immediate instruction in my instruction set, which in turn requires a register just to store another register. Oh, this is unexpected. Some instructions aren't supported. The offset for the epilogue is too far, so I need to allocate space for a full constant load in the prologue. I realized I can always place a full constant load that handles a 2-byte offset, so it will support plus minus 32,000. That should be more than enough for such constrained microcontrollers. I will change it to 4 bytes if a problem occurs, but for now I can leave it to bytes and save some space. And boom, we have the target executable. Now it is the time to crash it on actual hardware. And yes, I'm facing an issue with unimplemented system calls used by TinyC. However, my system call handlers weren't particularly well written. So I've redesigned the implementation to map IDs directly to function calls. So now instead of this huge block of system calls logic, I have a few lines that just call the handler from an array. Mapping between handlers and IDs is generated in compile time. Then each handler can be implemented as a separate function. The next issue is with elf section placement. I have no idea why raw data, which is read-only, ended after PLT. Do we have impostor inside relocations? Data relocations should only apply to RAM data. So I check on the internet, and actually raw data can contain relative relocations because we have to process that data somehow. Now I have two options. One, to keep the current relative relocations tied to the program counter, which forces me to place raw data section in RAM and process relocations accordingly, similarly to data relocations. Second is to modify the linker to generate global offset relocations for read-only data, but this might be too expensive. Each variable placed in raw data section would require a corresponding global offset table entry. Perhaps the best approach is to simply merge raw data and data sections and then place them both in RAM memory. But do I have enough RAM to run TCC? Most probably not. Since I don't have execute in place functionality yet, I have to load all TinyC sections into RAM, along with the memory that it uses in the runtime. So what do we need? At least 500 kilobytes just to load TinyC compiler into RAM memory. So I added support for the QMI interface, which had one of the hardest to resolve problems. I had the wrong timings, but not for PSRAM memory, but instead for flash chip. This was very hard to figure it out. Alright, that's not part of that video. Then I've implemented support for text and data separation inside TinyC compiler. It's a huge optimization, since I no longer need to copy code from flash to RAM memory. Only data needs to be allocated in the runtime. And thanks to that, I have real support for shared libraries. Multiple instances of the same library use a single text section block inside memory mapping, and differs only with data section for each of them. Last feature necessary to run TCC on the target was adding support to YAV file format in the linker. After that, TinyC is self-sufficient. I no longer need this mkimage Python script. Of course, I had more issues to solve, but most of them was really similar to the ones that I already showed to you. To make the demo interesting, I even created a simple VI text editor clone. So let me show you a C compiler on a microcontroller. And boom! It compiles and it works. I have a fully functional compiler running on a microcontroller. So, can I drop my PC and use entirely my new hardware? Not yet. Not right now. I have only RAMFS, which supports writing files, and a very limited NOR flash chip. Plus, I still lack support for video output and keyboard input. In my previous video, I asked which topics should be explored in more detail. So what's the winners? Virtual file system, vScheduler, and of course, Doom. So here is the plan. First, I need to add memory card support. So the next video will cover virtual file system in practice. Then I will fix the scheduler to support idle tasks and sleep modes. In this phase, I will also dive into process management and scheduling, and after that I will attempt to run ASCII Doom. If that fails, I will shift focus to VGA and keyboard support to run a real Doom with GPU support and graphics and the other stuff. Alright, that's all for today. I hope it was fun to you and see you in the next episode. Bye!